Andreas Dress from the Chinese Academy of Sciences, who will speak about recent progress in phylogenetic combinatorics.
Thank you, and thanks to the organizers of this wonderful conference, and also all the weeks we had before here to work quietly and intensely on the topics we are most interested in within the context of phylogenetics, which is phylogenetic combinatorics. Now, nobody here will deny that there is phylogenetics and that it makes sense to study phylogenetics. But why is there phylogenetic combinatorics? Maybe that's not so obvious. But luckily, I have Jack and Kati and Vince on my side. They believe that this is a good discipline to study. So if you disagree, you can discuss with them as well as with me. So according to our point of view, combinatorics deals with the combinatorial aspects of phylogenetic tree reconstruction. And after all, if you look at what you are doing, you have a big set, the sequences or the species or whatever, and to construct a system of subsets. Now, nothing could be more combinatorial than just a set with a set system. So therefore, of course, there are combinatorial aspects in phylogenetic tree reconstruction to construct such systems. But for phylogenetic combinatorics proper, the following observation was a starting point. Given a metric D representing the approximative genetic distances dxy between the members of a finite collection f of taxa. So yesterday you heard that maybe we shouldn't call them distances, but what was the other name? Divergences or whatever. I don't really mind how you call them. I just assume them as God-given or biologist-given. The biologists give them to us like God, and then we want to find out what we can say about this finite collection of this metric on this set X. And it was shown in the following that the following assertions relating to the object of desire. The object of desire is, of course, a phylogenetic X tree, and you also heard definitions of what a tree is, what a phylogenetic tree is, phylogenetic X tree. I don't think I have to define it again. Does anybody want a proper definition of phylogenetic X tree? Okay, I won't bore you with that then. So the following assertions are all equivalent. First of all, the so-called tight span of D is an R tree. Now maybe some of you would need a proper definition of an R tree, but I'm not going to give a proper definition, only an intuitive one. Think of a tree. You may want to think of that in terms of a graph or a graph with edge lengths. But if you draw it, this graph has not only its vertices, it has also points along each edge, each branch. And altogether, this, from a topological point of view, is a tree. Not just the vertex set is a discrete set, but if you take all the branches as points, and you can really make a metric space. If you have some point on a branch, you give it distance. You just measure how long it goes to one vertex to the other vertex, and to any other vertex, you take this length plus the distance of this vertex to the other vertex. So clearly, all the points on a tree, if you draw it, if you don't think of it in this abstract graph theoretical way, form a metric space, and such metric spaces are called R trees, and they play an important role in group theory, for instance, whatsoever. But what is a tight span? Given a metric D, you look at the following thing. You look at all maps from X into R for which Fx equals the supremum over all y of dxy minus Fy. Now what does that mean? That means basically Fx is larger equal to all of these expressions and equal to one of them. But larger equal to all of these expressions means Fx plus Fy is larger equal to the distance of X and Y. Okay, and the other thing, but for every X there is some Y where equality holds. That's just the definition, and why it makes sense you may see a little later. I'm not going to motivate it. The second assertion is there exists an edge-weighted X tree. Now that's the X tree as you know it. So it has a vertex set, it has an edge set, and it has a length assignment net L. a finite tree with vertex h set E such that V contains X. Every vertex in V minus X has degree at least 3, so you now get the definition of an X tree after all, and a positive H weighting L that assigns a positive length L of E to every H E in E, such that D is the restriction to X contained in V of the shortest path metric induced by A, L. If you have a graph and you have weights on the edges, you always have the shortest path metric. You can describe it in terms of passes and their total length and doing the shortest. Much easier, it is the largest metric on D, such that the distance relative to this metric D between U and Y is smaller or equal to LUY for all UV in E. This is just the shortest definition of the shortest path metric. Maybe not quite familiar. Next, there exists a map W from the set of all splits or bipartitions AB of X into the set of non-negative real numbers, such that given any two splits S and S prime with positive weights, at least one of the four intersections, A intersected A prime, B intersected A prime, A intersected B prime, B intersected B prime, is empty. You know, this is it. I mean, if you classify animals, okay, you look at mammals and vertebrates. So it's okay that there are every mammal is a vertebrate, which means that the intersection of the set of mammals with the set of non-vertebrates is empty. So the split mammals non-splits, the split mammals non-mammals, and the split vertebrates non-vertebrates has an empty intersection. Or if you look at mammals and birds, okay, the split between or the intersection between mammals and birds is of course empty. So always something is empty, and this has something to do with the whole thing coming from a tree. And the other thing is, of course, it has to be related to D. If I take the sum over all splits that separate X and Y and their weights, then this is dxy. So this is yet another assertion in terms of splits, and of course people refer to such description of phylogenetic relationships here also. And finally, the famous 4-point condition, dxy plus duv. If I take 2 points xy, 2 points uv, and they take their distance sum, then this is smaller or equal than the maximum of the two other ones. Which actually means that of those three sums, the two largest must be equal. If one would be larger than the other two, I could sort of relabel xy uv so that the largest comes up here, and then this would not hold. So this just means that the largest of the three terms here are equal. Moreover, the matrix T space TD actually coincides in this case with the R tree that is canonically associated with an edge-weighted X tree. I told you if you have an edge-weighted X tree, if you take any point on any edge, there is a distance from this point to any other point on that tree if you draw it. So this is really then gives you the R tree, and this R tree that you get from this is just the same as this one. This observation suggested to further investigate the tight span construction, this TX construction, and representations of metrics by weighted split systems with various specific properties, not necessarily the two I mentioned before, even if the metric in question would not satisfy the very special properties described above. After all, I mean, the description in terms of the 4-point condition looked nice. Something is smaller than something else. It could be generic. But as I pointed out, it implies that of those three sums, the two larger ones must be equal, which is perfectly non-generic. So in general, if you take an arbitrary metric D, it won't satisfy this condition. And one of the problems, that's why I'm sitting here, is basically, given some data, try to find a tree, which means try to find such a metric. It's just the same thing. Okay, and representations by weighted split systems with very specific properties, even the metric would not satisfy the very special properties described above, one of those four. These investigations have in turn given rise to a full-fledged research program dealing with many aspects of these two topics. Okay, and here I will focus on rather new developments relating to block decomposition and virtual cut points of metric spaces that allow to canonically decompose any given finite metric space into a sum of pairwise compatible block metrics, thus providing a far-reaching generalization of the result recalled above. So above, if we have the 4-point condition, then there's a unique decomposition into split metrics and a unique graph that you can draw, which is the X tree and so on. But now, in this talk, I will just look what can I do if I have an arbitrary finite metric that is not necessarily has a 4-point condition. I don't want to approximate it by anything that has this property. That has been studied here yesterday afternoon, and that's very important work. But I just sort of sit back. I don't want to deal with an approximative approach to metrics. I just take them as they come, God-given or biology-given, and try to find out what can I do with it without trying to say that can't be wrong, that can't be right, it must be wrong. We have to correct here, we have to correct there, and see what it leads to. Of course, I'm very happy with all sorts of correction methods for distances that have been proposed because they provide new distances. And Adama, for instance, or whatever, provides, given some distances, new distances, and I can just work with a new distance as well. I just work with the distances as they are and try to find out something. Yeah, I think, yeah, okay, we go there. I must make one remark. I mean, recently in British television, they once again showed this very old movie from the 60s, I think, Bonnie and Clyde. You may have heard about that. You may even have seen it. You may not have heard it about at all. Anyway, it is in the Great Depression in America, and Bonnie, when she meets Clyde, she asks him, "What do you do for a living?" In this little western town in America, Midwest town. And he sort of proudly, sort of a little bit cautious, admits, "I'm robbing banks. I rob banks." And she is quite happy with that. She's quite impressed. So we have to admit we prove theorems. And also with a mixture of pride and shame, because I know in the context of computational biology and phylogeny, you do not necessarily need to prove theorems. You have to develop good algorithms that somehow deal with your data. You may not be so focused on proving theorems. But I'm a mathematician after all by training, and I would like to prove theorems. So I'm afraid that what you will see here will not the proofs of theorems, but I will try to describe to you a theorem that has been proven. And the whole point is that it can be proven. The fun was to prove it, to find it and to prove it. Okay. But I would still try to find some motivation, give you the motivation for this. So this is a network of fungi, and it was provided to me by Daniel Houston, who produced it with his marvelous software Splitstree. But of course, it's not a tree, it's a network, as you can easily see. And sort of these networks typically show up if you use one of those programs, NeighborNet, QNet, or whatever, for a given distance matrix or sequences or whatever. And so what is the metric that you see here? The metric is just, okay, the metric is just between any 2 points, the total length of the path from one to the other. Yes, this is what we want. But this metric is represented in this graph theoretical form, which has certain amazing properties. What you see is sort of, there are a number of points, like all these points on these lines. If you cut this point, then it falls apart. So it's what people call a cut point in graph theory. So there are cut points, but there are also sort of here, this thing here has no cut points inside. This is sort of a block. So from a graph theoretical point of view, you could decompose this graph into two connected components. That's what graph theorists would like to do in this case, because it has a lot of two connected components. What is a two connected component of a graph? Everybody knows? Or do you need an explanation? Who needs an explanation of what a two connected component of a graph is? One. Okay, and I will shortly do it. I mean, you know, connected components are easy to see. You say 2 points are equivalent if they can be connected by a path, and that's indeed an equivalence relation, and the equivalence classes are the connected components. The two connected components are not defined on the vertices. They are defined by an equivalence relation on the edge set. And you define two edges to be equivalent, like this edge and this edge, for instance, if they occur on a cyclic path. Yes, this would be one cyclic path. We also have another cyclic path that contains these two. This here would not be a cyclic path because we go through the same point twice. So there is no way to go from here to here, for instance. I mean, you could go this way and back, but this is, of course, not a cyclic path. So while these two are two equivalent, these two are not. And it is easy to see that this is indeed an equivalence relation. I mean, you have to look more precisely at the definition, but if you have one cycle on which this edge and this edge is, and if you have another cycle where this edge is and this edge is, then maybe you can combine these two cycles somehow to get a cycle that just contains these two. Something within the given cycle might just satisfy such a relation, and so that's an equivalence relation. So you have an equivalence relation on edges. You take the equivalence classes of the edges together with their vertices, so they may overlap, but they overlap only in single points, like here. This is one equivalence class, this is another one, this is another one. So they intersect in vertices, but never more. If they would intersect in two vertices, there would be one way to go here and there, another way to go here and there. Then they would be in the same connected component. And this decomposition is sort of what falls into your eye if you look at this. You see there are clearly well-defined these blocks of two connected components, whatever you want to call them. There are also some that have just a single edge. This is a single edge and it's already its own two equivalence class. Here you have something more and so on. But here again, this is just one class. This is another one, and this is a really big one. My feeling was when I saw these pictures that by analyzing in a systematic way the two connected components of such graphs could help us to understand the phylogenetic data. Because after all, what everyone would agree was that clearly this should altogether form something like a clade. This does not form a clade. They are single. We don't really know how they are related. These three should form a clade. And here we really have a tree-like, so everything on one side could form a clade, but there are smaller and smaller clades. Here, this is unresolved, you would also say. We have no way of resolving. The data don't allow this in a clear-cut way, so we give up on that. But we still we would get, that's another result about two connected components. If you replace sort of all the two connected components, each connected component, for each connected component, you add one more vertex. You connect it to all the vertices by a star-like fashion in the component, and you forget all other edges, you get a tree, highly unresolved tree. And at least you get something close to what phylogenetic people want to see. It's not a really proper X tree, it's highly unresolved, but it gives you sort of the information you are seeking for. And this amount of unresolving of still may help you to better understand. So all this group here seems to be not strongly connected to the rest, so maybe this is a good clade. Maybe this is not. But at least it suggests what is going on. So I was interested in the following question. Can we reconstruct this network and its blocks or two connected components from the metric it induces on the set of fungi labeled vertices? That is, what we have given is only the metric on these points, not the net. Are there many ways to construct such a net given the metric on the fungi? Is it unique? So what is the relationship between the metrics and all these blocks and the whole structure of the graph, the two connected components in here? And that's what block decomposition theory is all about. And indeed, somewhere in analogy to Dan Gusfeld's theory of gold trees, some of you may have seen, that identifies blobs in sequence space using median networks. Block decomposition theory allows us to identify the blocks within the framework of metric space theory. Yeah. And now I think I would like, I mean it's all here, but I think you can understand more easily if I now start working on the blackboard and trying to explain this one theorem I want to talk about. And how it generalizes there's some chalk. There's more. Very good. Okay. So we start with our set X and this God-given metric mapped from X to X into R. And the image of xy I will for short just write by xy, forget the d. That won't change all the time. What is you know that metrics can be represented by graphs. After all, the tree metrics can be represented by a graph that is a tree. What is a graph representation of a metric? This is first of all a graph with vertex set and edge set E, and a length assignment as before, as for the tree we had, but now it's not a tree anymore. Now it's a graph, arbitrary graph. It should actually better be positive. Negative edges we could as well forget. Such that X is contained in V, just as the X tree. Basically, it's almost the same as an X tree, only that we don't want that to be a tree, and we forget the special condition that the vertices outside X have degree 3 at least. But we still, given a graph and a length assignment, we have this shortest path metric as described before, and we want dlxy equal xy for all xy in X. So these are the conditions on a graph representation. Now, of course, clearly graph representations are not unique. There are many graph representations. You can always add vertices and so on. Of course, you want a graph representation to be as parsimonious as possible. For instance, you may hope that if you want the total sum of the edge lengths L of E, sum over all these, you want it minimal, and you would hope that this is unique. And indeed, if the metric is a tree metric, satisfies this 4-point condition or each of these 4 equivalent conditions, this is one way to describe the tree. It is a shortest graph representation of the metric on D. So that was why people getting interested in tree representations of tree metrics were thinking, okay, if the metric is not satisfying the 4-point condition, still we may look at the shortest point, shortest path, the shortest graph representation of the metric to get all the phylogenetic information that we can out of the given metric here. Now, it soon turned out that while on 4 points, the shortest graph representation is unique, already on 5 points it is not anymore. And Jack and Vince and other people did some more good work on this, trying to better understand this non-uniqueness phenomenon. So just looking for the shortest graph representation doesn't help much to get a unique answer for the questions we have in mind. Actually, people showed that there are not only finitely many, there can be even continuously many shortest graph representations on 6 points and so on. So it is not such a useful concept. But we can, of course, still modify the idea of graph representation, and we say a block representation. This is a block representation if and only if G is a block graph, or block realization. I think we call it realization. This is a block graph. Now, why does it make sense to make this restriction? First of all, trees are block graphs. Secondly, every other graph gives easily rise to a block graph. You just look at its 2 connected components and you make them cliques, because that's the definition of a block graph. A block graph is a graph where all 2 connected components are cliques. So if you have any graph, connected or not connected, you can look at the 2 connected components and any 2 vertices within one such component you connect by an edge. In other words, it means there are no cycles without chord except of length 3. If you have a cycle in the graph of length, say, 5, okay, these 2 are in the same two connected component because they are in the cycle. Therefore, these 2 should, the cycles, so the 2 connected components should be cliques. Every 2 points in the same 2 connected component are to be connected. So if we have this 5 cycle, we also have all these vertices in there. Are there enough? Not quite. We still need this, and so on. So you make complete subgraphs for every 2 connected component, and then you have a block graph. So if you think of the fungi network, it was not a block graph, but of course you easily spotted the 2 connected components. You spotted many parallelograms, for instance, and then you would just add these 2 things to get a block graph. Doesn't really, no big deal. So a block realization is just something where G is a block graph, but we want something more. You remember that for defining an X tree, you have to have some condition on the vertices that are not in X. The vertices in the vertex set of the tree that are not labeled by a species. They should have degree at least 3. Because otherwise, if you don't make this condition, they won't be unique. If I have something like that, here are the thing. If I can add vertices here, I can do it ad libitum, and there's no restriction to this. So they are not really informative. Of course, when things developed from A to B, there were all the species variants in between. But if there was no bifurcation, they should not go into the X tree we construct. So we need some more block realization. G is a block graph, and every vertex V in V has degree at least 3, as for the X trees, and that's not quite enough, and is a cut point of the graph. What is a cut point of the graph? A point that if I take it away, then the graph has one more connected component. If the graph was connected to begin with, we can always restrict our attention to connected graphs. If I have one point there I take it away, it decomposes into two connected components, then this point was a cut point. That's standard graph theoretic vocabulary. And we want all those points that are not in X to have degree 3 and to be cut points. That's a rather technical definition, but okay. If you are among mathematicians, you have to accept that we come up with our definitions and want you to never ask why we do it. Okay. So why are we interested in in block representations? Because the theorem I would like to explain, not to prove of course here, is that there is a canonical 1-1 correspondence between block realizations, as defined there, not too many conditions, and on the one hand, and on the other hand, compatible decompositions of D. This is the other concept that is apparently relevant in this thing. You saw already decompositions of D. If you think of the first theorem, we said one of the equivalent conditions was that the metric satisfying the 4-point condition is just a sum of split metrics. And the splits associated to this even had very special conditions that we called compatibility. So now I have here something similar. So what, first of all, is a decomposition of D? It's just writing D as a sum of other metrics defined on the same set X. If you think again of a tree metric, you see every edge gives rise to a metric, a very degenerate metric on X, because it separates the set X into two subsets. If I take it out, one subset here, one subset here, and if I say now I define a metric on X that gives distance 0 to all the points here, distance 0 to all the points here, and distance the branch length of this edge to any point here and any point here, then the total metric is just the sum of these split metrics. I mean, this was one of the fundamental observations that went into the first theorem I explained to you. And so that means in this context it makes sense maybe to ask for decompositions of a metric into other metrics. But there are of course much too many. There are thousands of decompositions, even more continuously many in most cases. So of course we do not want any kind of this complexity. We want first of all the I are linearly independent. That makes sense. I mean, if I have one and the same metric occurring twice with different scalars, we just put it together. The more, that has nothing to do with compatibility. This is only one of the two conditions. But the second thing, how do we define decompatibility? Now, first of all, if you have a metric, can everybody see here? Otherwise I can go there. Maybe it's nicer. I can still get away with it. It's only a side remark. But whenever you have a metric, you have an equivalence relation on X. Because you can say X is D equivalent to Y if and only if the distance from X to Y is 0, which is actually equivalent to the fact that XZ equals XY and equal YZ for all Z in X. And this is obviously seen to be an equivalence relation, but it's equivalent to this thanks to the triangle inequality. So this, some people say this is always the trivial equivalence. Only X is equivalent to Y if and only if X is equal to Y. Otherwise, it's not a metric. For instance, Michel Desa in his books insists on looking at metrics in this way. But while I'm perfectly willing to follow most of his advices he gives freely, in this case I don't, because really it is important in our context to have metrics where two distinct points can have distance 0. All the split metrics into which we want to decompose our 4-point metrics, of course, are highly degenerate, have many points of distance 0. So we are really interested in this equivalence relation, and we are also interested in the partition of X into equivalence classes. So this is just, so I could say X of D I define to be all the points in X with xy equal 0 that are equivalent to X. So this gives a decomposition into disjoint subsets, a partition, and this is a partition associated to D. Now in our case, actually, we may assume that D is proper, but we will not assume that these things are proper. So we will indeed assume that they are not proper and that these equivalence relations are highly different from the identity equivalent relation. So what we want to have is for all ij in 1 and to k with I not equal to j, there exists xij and xji in X such that di of y xij times dj y xj I is equal 0. That means one of those two terms is 0. This or this is 0. Now, that's a bit strange, I would assume. But if you think of compatible split metrics, compatible splits, if you have two splits that are compatible, that is, here is a split S in A and B, and the other split S prime in A prime and B prime. And if this is empty, this intersection of these split halves, then if you look at the resulting split matrix, ds and ds prime, you have one point, I guess it should be on each side. You have either, you can have x1, 2 and x2, 1, and then you would see from any point y anywhere, the distance from these points to this point is 0 relative to both metrics. The distance from this point to this point is 0 relative to S prime, because they are not separated by this. And the distance from this point to this is 0 relative to S, and so on. So you always find enough zeros among the distances. And if you think about how that can be generalized to more general sort of input metrics, the metrics that you want to have as your blocks inside your graph or inside your metric, this turns out to be just what makes things going. I mean, it's what, from mathematicians' point of view, makes these things natural is that really, after all, we will show that there is a 1-1 correspondence between block realizations and compatible decompositions. But maybe it's easier for you to think back of the fungi diagram. Yes, you see? How did that look? Sort of, you have all these blocks into which the whole thing decomposes. And now for each block B, I define a metric D sub B. After all, if I want to have a 1-1 correspondence, I must be able to go from block realizations to compatible decompositions and back. So how do I do this? This will also easily then tell you why this condition is natural. If I take this block, B and B prime, then are there points here such that for every other point, so yeah, first of all, some point y, what is the distance between y and y prime relative to dB? If y is here and y prime is here, there's always a first point in B if I go from y or y prime to B. This is sort of what people would call the gate of y in B, the first point I get to. In block graphs, this is always well defined. And if it's a point in here, it's just this point. If it's outside here, it's this or this or this. And then I define the B-induced metric to be just the original metric, d of yb, y prime b. So every block in a block representation defines a metric on the original set, but highly degenerate, because all the points over here on this side get distance 0, and so on. And similarly, I have a metric dB prime, defined with the things over here, which in this particular case, all the points out here have distance 0, and only the points inside B prime may have their not distance 0, they have their original distance. But if I now take, for instance, these two things, and I take this point as x b prime b, and this point as x bb prime, you will see that for every other point I take what do? I take the distance to this point, which would be this, and this. Why is that 0? Something should be 0 here now. I want
dB prime,
hmm?
dB prime, yb, x, y to xb prime b, and dB prime is 0.
The distance, yeah, okay. If I should be rather trivial. Sort of what it says is that the equivalence class of xij relative to I and the equivalence class of xji relative to j together are everything. The union is all of x. So what is the equivalence class of this point, for instance? This is everything over here. All these points over here have distance 0 with respect to these two. And the equivalence class of this is everything over here. So the distance of y with respect to this is 0, because this is actually the entrance point. The distance here is non-zero. And wherever I choose my y, whether I choose it here or there, to one of the 2 points, the distance is 0. Just some technical condition, but an important one. Here we can already stop. We don't have to list any more definitions. And then the theorem says there's a 1-1 correspondence between equivalence classes of these block realizations and compatible decompositions. Of the metric D. Two objects that the way they are defined do not seem to have much to do with each other, but I indicated already how I go from here to there. I take my block realization, and now I have to come up with these compatible metrics that together sum up to D. And these are exactly the metrics I get in this way. So if I have such a realization, I say dB of any 2 points x and x prime is just the original distance of xb and x prime b, where these are the two entry points, the gates of x and x prime in the block B. And in the block graph, you always have a first point, the closest point to the a given point in any block, and you take their distance. And you just can show that if you sum over all these things, that D is sum of dB over all the blocks in your block realization. Okay, so, and then you can show, I didn't so indicated how that can be done, because it's all the properties of this block graph. Block graphs are, on the one hand, everything gives rise to a block graph because you can just add enough edges. On the other hand, you can, they are almost tree-like. I mean, if you contract the blocks to points, or just rather not to one point, because then everything might be contracted, but you just import one point and connect it like that, then you get a tree. So they have this tree-like fashion, so that these points are really well defined, the first entry points. So this is how to go from block realizations to compatible decompositions, and to go from the compatible decompositions to block realizations. This is also not very hard. This is somehow you mimic what you do if you want to go from a compatible system of splits to the tree that represents all these splits. And sort of what you do there is what we call the Buneman construction. Sort of you just look for assignments. In this case, every split is assigned alpha as a subset of the two sets in S, such that alpha S intersected alpha S prime is non-zero for any, non-empty for any SS prime in your compatible split system. You look at all of these assignments, and they form the vertices of the tree you want to construct, and two vertices are connected by an edge if they differ only at one spot. And you can exactly translate this into this context here. You have not, the only difference is that we don't have splits, we just have these partitions. But still, I can map every partition to one of its sets, but so that whenever I have two partitions, the intersection of the associated sets is non-empty. And I make them the vertices of a graph, and I connect two things if they two such maps if they differ only at one spot, and then I have a graph, and this is a block graph in this case. Or you can construct from this a block graph. So these are standard constructions that have been tried out already in the context of split decomposition theory and studying the relationship between compatible split systems and trees, and they work in this generality. So what we after all get is we get a general theorem on that works for every metric. We don't need 4-point condition. We always have given a metric there is this 1-1 correspondence. Now, maybe there is no compatible decomposition. Then there is also no interesting block graph. It will only be one block. Okay, that just happens. You can't, certain metrics are undecomposable anyway. And so we can, a metric we call a block metric if it cannot be decomposed into at least two ways. And then the main theorem, of course, now says that every metric has a unique decomposition, compatible decomposition into block metrics. This is what, from this correspondence, this is what you can derive. Every metric has a unique decomposition into compatible decomposition into block matrix, and that generalizes exactly what you know for 4-point metrics. You know every 4-point metric has a compatible decomposition into split matrix. And so this works for every metric. Is it useful in phylogenetic analysis? You see, generically metrics don't satisfy the 4-point condition. So all this analysis has not been, could not be applied directly to phylogenetic data. We were doing it one way or the other to still cope with it. Of course, generically, it's even worse. Generically, every metric is a block metric. So the block decomposition won't do much. But first of all, you still see block decompositions when you use QNet or NeighborNet and so on, and you construct something to the given metric which is not quite the metric. So which means there are, if you want to approximate a metric by a metric that has a good decomposition, though not necessarily in splits, that will be much easier than approximating a metric just by a 4-point metric. Let's say a tree metric. So I think it has a potential still to be applicable in the context, and gives you a little bit more freedom, not always to look for the real object of desire, which is the phylogenetic tree, but just for maybe identifying certain clades within your set of species given the distances. So as you see, this is still work in progress, and 2 or 3 papers are out, and but we are happy for every paper that is not yet out, because we are rewriting it and then we can still change it. If you want to know more about this, you can ask me or Kati or Vince or Jack to get more detailed information, and you get on the mailing list when we really finalize our papers. But I think sort of what I wanted to emphasize is that while these mathematical theorems you can prove in this context are almost never ever really directly applicable to the data we get from the biologists, they set a conceptual framework that might be helpful, and from my point of view, they're just beautiful results. I mean, as a mathematician, you really like to have unique decomposition in something indecomposable. I mean, I come from group theory and representation theory, and you know that every representation of a group, finite group over complex numbers, is uniquely decomposable into irreducible components up to isomorphism, and so we have very similar results. So that's what I like about it. Thank you.
Are there any questions?
When you're talking about the metric on trees, then you have 4-point conditions. And but then when you're talking about the matrix on networks, what's the condition?
None.
So you mean every matrix can correspond?
I can play this game for every metric. And every metric decomposes into its blocks uniquely. And, but very often it's itself a block metric. So there's nothing that can be done about that.
So this network actually is a graph, I mean, realizations of this matrix.
Yeah.
Other questions? Yes.
Here, once you get your blocks, is there a way to continue decomposing and try to do something inside of your blocks to avoid having cliques and going further?
Yes, of course. I mean, given any kind of metric, we developed split decomposition, which is not block decomposition. We just try to write a metric as a sum of splits with some term that we could not deal with. For the block metrics you get, you can of course then apply split decomposition and get further insights. So this is surely possible and should be done. I mean, it's on our program.
Do you have any intuition or idea what could happen if you relax the assumption on the additivity hypothesis on the distances? What could happen? How your model could be modified, or what do you think?
Yeah, sure, we do. We can describe. So if you have such a diagram, and then it suggests, this suggests that this is a good cut between the species in question. But maybe really the diagram looks like that. Here you have more edges going over. So this still looks like a good cut, but it's not a cut according to our current theory. But somehow it is up to epsilon. So these things are epsilon apart. Up to epsilon, it is a good split. So we define a split AB to be an epsilon split. I mean, a real good split is that AA prime plus BB prime is smaller equal, it's actually smaller than the maximum of AB plus A prime B prime and AB prime plus A prime B. Could also say minimum whatsoever. Now I relax this for both possibilities. So there are some theory deals with minimum, some theory that deals with maximum. I relax this by saying plus epsilon. So more or less that splits in a nice way. If that happens for all AA prime in A and for all BB prime in B. And what we really, for this relaxed situation, want to study are the epsilon splits. This is also work in progress, but it's much less progressed yet.
Let's thank Professor Dress again.